This is just a test, Jerome. Just confirm me if you can hear me.
Hi, Ramis. We can hear you loud and clear, at least from my side.
So hello everybody, so we can continue to the second presentation of this day. So before starting, just to call you back to remember you a few elements. So the presentation are recorded and you will have access to all the recorded videos and PowerPoints or PDF at the end of the conference, so you will get more information concerning that later. And also, you can ask any question you have on the presentation during the session using the interface of GoToWebinar. So send your questions, and at the end of the presentation, we will take a few minutes to answer to the different questions. Thank you very much. And now we can start the second presentation performed by Aramis Chouanka-Trevisan from Enercon. So the topics of the presentation is the assessment of interactions involving wind farm systems. Just few information on Aramis. So Aramis Trevisan is working now in Enercon, Germany. So he received his diploma in engineer degree and master in the Leibniz University of Hanover in Germany with a specialization in electrical power system. And then he joined the research and development team of Enercon in 2011. He has been involved in several grid integration studies and R&D projects addressing the grid integration and controllers of the Enercon wind turbine. And since 2015, Aramis has also been giving some academic perspectives to his research project while pursuing a PhD degree at the Polytechnique Montréal in Canada. And Aramis is also an active member of the SIGRE, and in particular the SIGRE working group B462, connection of wind farms to weak AC networks. And he is also currently supporting the activities of the working group B4C4.52 and C449, which are focusing on converter interaction in sub and super synchronous frequency. So now I will let Aramis perform his presentation. So Aramis, I will activate your microphone and give you the right to present your screen. Aramis, can you?
Yes, I am. I
Okay.
can hear you. I'm starting to share my screen. Just a second.
I can hear you.
Can you? Okay. Can you just confirm me that you also see my screen?
Yes, we can see the first page of your presentation. So you can start.
Okay. So thank you, Jérôme. Thank you for the introduction, and also hello everyone. It's nice to see you today, and I'm very also happy with the interest in my today's presentation. I will do my best to keep the high level of presentation as Hani did before. As Jérôme said, the title of my presentation today is Assessment of Interactions Involving Wind Farm Systems, and this is the opportunity that we have to share some of the results that we obtained in this joint research work between Enercon, which is a German wind turbine manufacturer, IREC, the Institute of Research of Hydro-Québec, Hydro-Québec as well. We have Martin Factour from TransEnergie on board, and also the Polytechnique of Montreal. So for you to be able to follow also the course of the presentation, here's the agenda. I will provide you first some context for our work and also present you the motivation. We're going to talk about the technique we are proposing to assess the small signal stability of large-scale multi-converter systems. We will go to one example that we prepared on a large-scale grid. We're going to talk about the stability assessment that we did for this particular case and present some validation of these results, which are conducted with detailed models in EMTP. And then at the end, of course, we're going to draw some conclusions. So let's start with some context for today's presentation. And I have to say, I thought a lot about what picture to put here at the beginning. I'm pretty sure that you have seen in other presentations years before, recent years, that there's this exponential growth of solar and wind in several power system jurisdictions. But I think it's always important to refer to the price of energy which is being offered nowadays from solar and wind, particular wind for today's presentation. And I put here a picture that I found, a graph that I found from the International Renewable Energy Agency, IRENA, from a report they published in 2019, in which we can see how significant the prices offered in auctions from solar and from wind have reduced. I mean, it's huge in the case of solar, going from about 240 in 2010 to almost 50 in 2018. And in the case of wind as well, we're talking about close to 100 at the beginning of the decade, and then in 2018 we have some auctions as low as 50, and we do know from some particular projects in which the auction value was around $30 per megawatt hour. So you may be asking your question, why am I saying this? And I just want to make the point that nowadays wind and solar energy is as cheap as other types of energy resources, of energy generations. Specifically talking, for example, in the case of Europe, it's important to mention that it's even cheaper nowadays than brown coal and hard coal and gas. So nowadays, it is not a question anymore of going green or doing something against the climate change. Of course, this perspective has to be there for the years to come, but it's also an investment question. As long as wind and solar remain cheap, this is also an investment thing. People will keep investing on this. They will keep shifting from coal, gas, and other conventional resources to these ones that are cheaper. So basically, engineers in this field, they can be sure, because of these prices, that we're going to be talking a lot in the years to come about large-scale integration of photovoltaic, and again, particularly also wind. So to keep up with the context of the presentation, we have also, as wind turbine manufacturer, have been observing some tendencies in the wind energy sector. First of all, we're still seeing turbines getting bigger and wind farms getting larger. Some years ago, I don't know, 5 to 7 years ago, we were usually talking about 2 megawatt turbines with a rotor diameter of 80 to 90 meters, whereas nowadays the projects that keep us busy here are of turbines in the range of 4 to 5 megawatts, and we're talking about rotor diameters of 150 meters, sorry. And I don't think we're going to stop in there. Even if we're talking about onshore, I think there's more to come in there, and we're still not able to see the size of turbines and the size of wind farms to stop. Second, also because of the increasing price pressure, I was talking before about the levelized cost of energy, which is a very important indicator nowadays for successful projects. We're now being forced to go search the energy where it's available. In the case of wind, of course, we need to go to wind-rich regions. And of course, this is where it makes sense to put wind farms and wind turbines. But it's also because it makes sense in bringing the energy costs down. On the other hand, I have to say that and I always like to show this picture, we and our ancestors, we don't like much wind. And specifically in the case of our grandparents and grandparents, they decided to settle in regions that are not wind rich. Meaning that, for example, I have here in the figure of the right, the wind map of Germany. We're going to probably you know, but the most dense, the most populated areas of Germany are the ones I'm trying to circle here. So you're going to have Berlin in this area here. You're going to have like the region of Rhine. Here you're going to have the Bavaria, Munich here. So you see that people decided to settle in areas that are not wind rich. On the left side, you have a similar case for the region of Quebec in Canada. Montreal will be, if I'm not mistaken, somewhere below here, which is green, which is not very windy, indicated by the green color, and the most of the wind parks, or an important part of the wind parks, the wind farms that they have in their systems, are connected to what they call the Gaspésie Peninsula, which is indicated here. So the wind farms that are connected here, they have to go like through long transmission lines to reach the load centers, which for us engineers means that we're going to have to face some technical challenges during the interconnections. Long transmission lines usually reduce the short circuit capacity, which means that wind turbines connected at the very end of this peninsula, they will face low short circuit ratio, so weak grids, and there's also some other challenges associated with the use, for example, of series compensation, and these all make the integration of specifically of wind very, very interesting. And we're not alone today talking for Enercon. We have also other players there. The one installing is the one offering the lowest energy costs, and we are sharing in these grids here in Germany, in Canada, and some other countries, also the grid with some other manufacturers. We have other wind turbine technologies, other controllers. So the complexity of power systems today is increasing, and it's changing also very fast. So that I took a picture from this IEEE transactions paper, which was presented by Hydro-Québec already in 2012. And this is, so they showed a detailed system from this from their grid, and you can see here, I hope that you're able to see well on my screen, you're going to have like different wind farms connected to different parts of the grid, different manufacturers. You see here Enercon, you see also Repower, which changed their names to Senvion. You're going to find also GE, and not only wind farms, you're going to have also some DC interconnectors, the ones shown here below, and you're going to have also some other equipment, for example, synchronous condenser connected to some portions of the grid. So the grid, as you see here, is very complex, is a multi-converter system. And now the question is, supposing that we are a planning engineer here and we want to connect a new system to this, is it still possible to make a statement about the stability, at least about the small signal stability, and is it still possible to assess the stability in an effective manner? So that was pretty much the motivation of our work. We were trying to put ourselves in the condition we want to keep increasing the wind share in the system, but we see that the complexity is increasing. How do we deal with this? And we have also seen reported in the literature from the last years, from recent years, that some events regarding wind have been reported, some adverse events. One very famous one is the one from 2009 in ERCOT, in the region of ERCOT, Texas, in the US, in which they have, if I'm not mistaken, about like 0.5 gigawatt of wind connected to the substation of Ajo. And there's one line from Lone Hill that tripped, and these wind farms remained radially connected to Rio Hondo. And in about less than a second, they observed like increasing currents going to almost 6 per unit of the rated values, and led actually also to some damage to the wind turbine existent in there. From this case, many publications, many works have derived. People started investigating what happened there, how can we deal with this, how can we solve this issue. And it's interesting to note that still almost 10 years later, in 2017, ERCOT reported some other events, at least 3 new ones, which are similar to the previous one. So still 10 years later, this is something that is still bothering some system operators. In these cases, there was still some line that tripped, and some wind farms that remained radially connected to series compensation, compensated lines. At this point, I have to say series compensation is a standard, almost a standard solution that power system operators use to improve system stability and reduce losses in the transmission way. But it's interesting to see that, again, almost 10 years later, there was still similar issues happening in the system. And this time with better transient recorders, we have also the figures of the currents with high transient recorders, and also an FFT of the current measures. And we see here that we have the 60 Hertz, the fundamental component, and also another component at around, I would say, 25 Hertz that was even more important than the 60 Hertz that was monitored in this event of 2017. We have also seen in the literature some events being reported for China. Many, I have to say. I had the opportunity also to talk to a colleague from China, and he said that it's more than 100 what they experienced in there. But I would like to call your attention particularly to this event in the province of Hebei in China, in which they have, I noted the numbers here, it's amazing, like almost 3.5 gigawatts of wind farms connected to this 500 kV substation. And I have one of the transient recorders data here from this paper, and you see here that in one of the cases, this is the power of one of these lines, was injecting about just a bit more than 200 megawatts, and some oscillation started and ended up tripping the wind farm. And when we look at the frequency of these oscillations, they were able to find the 8.1 hertz, and also the mirror frequency at about 92 hertz. So there are also other events that were reported in the literature, and I want to call your attention if you're interested in finding more of these events. Recently, there is this this IEEE task force published this new report, this new technical report called Wind Energy Systems, Sub-synchronous Oscillations, Events and Modeling. And I think it's worth it getting a look on what is there. You're going to find some other events and some other state-of-the-art techniques and ways of understanding and dealing with this issue. But to go back to our motivation, if we go back to that person which is responsible for connecting a new wind farm in that very complex system, we still need to answer this question. Is there still a way of efficiently identifying interaction risks? And when we do this, we tried to take also the industry perspective into account, because in the real world, we don't have much time, we don't have much resources available as we do in the academia, in the university, for example. And this leads to the issue that engineers, they have to deal with several projects at the same time, and then really don't have the time to go there and develop all analytical equations for their complete systems and investigate, for example, the stability, the small signal stability through modal analysis. This is just not possible. Also because it's a standard practice in the industry to use protected models. So if we would take, for example, a portion of the system, this is a standard figure that some planning engineer would be seeing. He's going to try to click on that wind farm to see what's behind that point of connection, and well, he's not going to be able to see what's in there. So this gives planning engineers also limited insights of what is going to be connected in there, operating engineers as well. And of course, this limits the amount of analysis that they can use in order to assess and address the small signal stability. So we try to take these perspectives into account, and we came up with a new technique, which we were calling the DQ scanning technique. I'm gonna talk about the details in the next slides, but you may find some interesting insights of this technique and some and the analytical validation of the technique, as well as some important considerations that you have to bear in mind when you're applying the technique into account. So this is a recent publication also from, I don't know, 1 or 2 months ago, and this is what I'm going to be outlining for you today here. So we're calling this the DQ scanning technique. It's based on an analysis in the DQ frame. We decided to go with the DQ frame here because we wanted also to validate the values, what we were obtaining from the black box models that we were also considering. we wanted to validate these results with analytical ones. So we took also some realistic converter models, which were also validated against manufacturer measurements, and from which we also had the information about the controls and the internal parameters of the wind turbines, and we were able to validate that with the DQ frame values that we were obtaining from the DQ scanning technique. And because the converter controls are usually done in DQ frame, this also helped in this validation process. But more important than that, in the DQ frame, and this is also outlined in our paper, it's also easier to find couplings between channels. And we're going to discuss this later on this presentation as well. So first of all, how do we apply this technique? And we took one simple example here. So it's still not the large scale grid that we want to show, we want to talk today. So we first took a very simple system, and we're supposing that we want to connect this wind farm to the grid. So we have here a simple representation of the collector system, the substation transformer, also some grounding transformer and some surge arresters, and we have the PCC of our system. So what we do first is that we have to define, again, this is a small signal stability technique, so this is valid for one operating point. We have to find for which operating condition we want to investigate. Usually this is done, at least at the beginning, for the nominal wind conditions, for which the wind turbines, they will be injecting the nominal power. And then we we choose a partition point, which is usually the PCC, and we divide the system in two. And since we are dealing with everything in the DQ frame, what we do here is that we start a time domain simulation, and we wait the system to get to a steady state condition, and then we extract the VD0 and VQ0 and the ID0 and IQ0, which are the current and voltage measured at the PCC. The currents flowing into the grid and the voltage measured at the PCC. And as you see here, this is the division was done in this case, separating like the wind farm that we want to connect from the grid. And at the grid, we can put anything here. We can also have some other converters. We can also have some a more complex structure than the one shown here. And then what we do is that we perturb the system in the DQ frame. So we take that VD0 and VQ0 condition that we took from the steady state condition, and we add to that some VD and VQ perturbations. But important to say, single tone perturbations. We first perturb the D axis, and then after we perturb the Q axis. It was not the goal of our investigation today to perturb both axes. This may be possible. It was not our goal until now, but it's something to keep in mind in order to eventually even accelerate this process. And then after we perturb the systems, we measure the voltage and the currents at the point of connection. We transform them back to the DQ frame, and then we extract for each perturbation frequency the D and Q input admittance of the system. So keep in mind, we are perturbing the system voltages, and we are measuring the current. So in this case here, we are extracting the input DQ admittances of our complete wind farm system. And you can have here more than one turbine and a very complex configuration of your collector system. Whereas in the case of the grid, we suggest to use current perturbations. The reason for that is explained in our paper, but to make it in short here, we have to consider in this small signal analysis, we have to provide a statement on the amount of unstable poles of each of these subsystems, so either for the wind farm system or for the grid. And the best way of doing this statement is by perturbing the grid with current and seeing the voltage. We show that in our paper as well, because if there is some unstable mode in the open loop system on the left side, on the grid side, we should trigger this with these perturbations in the current. So we perturb the current when we're talking about the grid, and we measure the voltage. And when doing this, we transform them back, the ABC values, to the DQ frame, and then we extract the ZDQ input impedances of the grid. At the end of the day, this is something that was already also in the literature. Our contribution here was also going towards the consideration of realistic systems. And when we were applying this technique to transformers for which the saturation is considered, when we were applying this, for example, to Type 3 turbines, in which the rotor control of the DFIG machines also play an important role in their small signal input dynamics, we were able to find that very low frequency perturbations were actually pushing the system away from the operating condition that we wanted to investigate. So there are some considerations that we have to take when applying the perturbations. We came up with a signal that looks somehow like this. So we basically lift the system. So this is just a perturbation signal that we apply on top of the VD0 and VQ0 if we are talking about voltage perturbation. And what we do is that we ramp up the perturbation. Instead of applying a stepwise perturbation here, we ramp up the perturbation, we hold that for a second, and we're gonna make the frequency analysis just for a small window of the signal. And by doing so, we were able to avoid several phenomena, for example, triggering of transformer saturations when we are applying low frequency perturbations, and also some other stochastic issues that we have when analyzing just a window of a portion of the perturbation signal. So we suggested using this signal. There may be other solutions that also aim at an improved computation speed, but this is the one that we suggest for the perturbation, and for which we also obtained good results whenever considering like realistic systems. Also important to bear in mind the result of this perturbation when we're talking about perturbations in the DQ frame. So we're going to be perturbing VD and VQ voltage, for instance, and we're going to be measuring ID and IQ. We're going to come up with 2x2 matrices for each frequency. And now the question is, how do we apply stability assessment on this? And we're going to still make use of the well-known impedance-based stability theory. However, in the DQ frame, what we're going to be extracting is the input admittance of our wind farm, which is illustrated here on the right side. And we're going to be extracting the input impedances of our grid. And we're going to be connecting them to each other. And what we suggest to do, something that has also been suggested before, is to use the generalized Nyquist criterion. When applying this criterion, it's important to make a statement about the right half plane poles of each of the systems separately. And for this, we use the statement that if the DQ scanning is possible, if you apply the voltage perturbation for your wind farm system and the current perturbation for your grid system, and the system was able to withstand these perturbations where no stability was triggered, then we are able to make the statement that they don't have controllable or observable unstable modes. And if that condition is valid, then everything that we need to do is to plot the generalized Nyquist criterion for the system and see if this is crossing, if this is encircling the critical point. If the diagram encircles the critical point, this goes back to the typical Nyquist criterion, then the system is supposed to be unstable. And we suggest then performing the detailed analysis in the EMTP to verify these results. So what we're going to do here today is apply this technique for a realistic system. So this system here you should have also available from the EMTP demos. It's based on a real system. You're going to find here 5 wind farms. I'm trying to indicate with my mouse here for you to see them. You're gonna have long transmission lines, which are also series compensated. You're gonna have also HVDC systems in here, and also other connections to other system representations, and also synchronous condensers. So it's a very large system. It's a realistic system. The parameters used in this model, they are based on real components. And again, it's a multi-converter system. And what we're going to be doing here today is we're going to put ourselves in the position of investigating the interconnection of a new wind farm. I'm going to be calling here the wind power plant number 5. So let's put us in the condition of investigating the small signal stability of this wind farm. I hope that you can see here, this is supposed to be connected at the end of the system, which is also series compensated and has also a low short circuit power here. And we're going to be investigating this system for 2 operating conditions, not only for the nominal operating condition, but also for another one, since we have seen also in our research that the input admittances of converters, they are also very dependent on their operating condition. So we're going to be showing this here. So we're going to assume, first of all, that we're going to have nominal wind conditions. So in the specific case of this wind farm and the models of the system, we're going to assume that we have 11.2 meters per second, and the wind farm is injecting full power, something around, if I'm not mistaken, 300. No, sorry. I think 200 megawatts in this part of the grid, and then we're going to be investigating the small signal stability for a low wind condition. So just as a reminder, the power goes with the cube of the wind speed. So when we go from 11 to 8, we're reducing a lot the power injected by this wind farm. So we're moving really the operating condition of the wind farm to another completely different one. So when we apply the technique that I outlined before, we're gonna do like this. We decided to partition the system at the PCC. That's going to be usually the case. There are some specific cases in which we suggest doing it differently. For example, in the case in which we have a voltage control directly at the PCC, then we suggest going one node away. But in this case, we were able to take the PCC as a partition point, and we define then what is the grid, which is going to be this full system here with the other 4 wind farms, HVDC, series compensated lines, and so on. And we're gonna investigate the wind farm. So it's, sorry, you can see here now, so it's about a 330 MVA wind farm. And we choose so we're gonna analyze both operating conditions, so with the nominal wind and with the low wind, and we're gonna plot the generalized Nyquist diagrams for these both figures. And well, they come up as these fancy curves here, but it doesn't matter how they look like. What is interesting was what happens around the critical point, which is the -10. And so if we zoom in here, in the case of strong wind, we can see here that we are not encircling the critical point, which means for us that we are not expecting any small signal stability issues for this condition. Whereas when we perform this investigation for the weak wind condition, so the figure looks similar, but if we zoom in around the critical point, we see that we are encircling the critical point. And this is the condition of our approach to indicate a possible interaction risk. And we verified this with detailed EMTP simulation. So basically what we did is that we initialized our system at the nominal wind speed. So we can see here the power injecting to the system. We have close to 1 PU. There are some losses in the collector system. So anyway, we are starting with a wind speed that is higher than 8, close to the nominal wind speed. And then after a certain point, we're going to reduce the wind speed, bringing the system to that condition of 8 meters per second. And when we do so, we see here that we start injecting less power, and at a certain point, around time equals 12 seconds, we reach that condition that we investigated before of 8 meters per second. And then we see here that we have growing oscillations. And that validates pretty much the results that we obtained before with the DQ scanning technique. So some conclusions. We see here that there is, we saw today that there is an ever increasing integration of wind and solar plants in the system. And there is also an increasing need of investigating the systems. Of course, some of them related to the challenges associated with connecting the systems to portion of the systems that are weak or that have other converters around. We outlined a technique that we suggest for the use, which take into account some industry constraints, which is the limited resource and the tight project timeline. So it's something that can be done fast. You can screen out the input admittances of your wind farm, and you can screen out also the input impedances of your grid, and you can perform this analysis, this generalized Nyquist criterion analysis to assess the stability. And we showed how this is done with the DQ scanning technique today, and we demonstrated today here for you that its application in a large-scale grid was successful and was able also to identify a specific small signal instability case for a low wind condition for that wind farm number 5 at the end of the grid. So that's my presentation. Thank you for your attention, and I am willing to take your questions. Thank you.
Thank you, Aramis, for this very nice presentation. So now it's time for your questions. So you can ask your question in the interface of GoToWebinar. So you have a section called question to send your question. So first we have a small question regarding, I think, the beginning of your presentation. So the person saw a series capacitor in your model and asks if it is used for the frequency regulation or another use. Did you hear me, Aramis?
Yes, yes. So I was reading the question. So you suggested me to read the question and then go.
I can read the question to
Okay,
let
yeah.
the question
The
to
audience.
everybody and then you can answer.
Mm-hmm.
So what was the purpose of this series capacitor in your model? I think it was in the model when you connect your wind farm to the power system.
Okay, so are we talking? I will assume that we are talking about this series capacitor here.
I think yes.
Yeah. So in both cases, so because I demonstrated the DQ scanning application for a simple system before, so this one here, which is a 230 kV grid. And in this case here, so the question is, what is the value of the series compensation, right? Or what is the purpose of the series compensation? So the value of the the series compensation was such to have a series compensation in this case of around 50%, and this is also similar to this large scale grid. So the line impedance here, so the series capacitor here is used to improve the transfer capability of this point where the wind farm is being connected to the rest of the system, but also to improve system stability. And in this case, the series capacitor was chosen to have a value of around 50% series compensation. These values in real case, if I'm not mistaken, they're going to vary between 25, 30% to not much more than 65%. So this is going to be the range, and they're going to be there to reduce this electrical impedance between your generation point and the rest of the grid. So usually what you're going to have is a long transmission line here, and we're going to use the series capacitor to reduce this electrical impedance. Okay.
Okay, thanks. Another question. So have you noticed any first swing instability case using this method?
If I was able to note a swing, can you repeat the question, please? A swing?
I think the question is, did you process this new method in real case, and did you notice any
Yes,
instability case?
yes. So that's well, we didn't have so that's a very interesting question because working for Enercon as well, for the R&D, we were actually hoping one day to have such a case in which we can apply this, but we were able to make some investigations, realistic systems in which we triggered the parameters of our turbine controllers or changed also the grid impedance and some grid conditions. So these were fictive cases, but based on real turbine controllers and turbine parameters, and we were able to successfully apply this technique to these cases. However, I have to insist that the figure that you're seeing here, this case, which is again available at the EMTP, this is a realistic case. This is based, I think in the EMTP, it's also called like this. This is based on a real system from Canada, and I assure you that the values that we were using here, they are very realistic and very close to the ones that people have in their real system. So yes, we apply this to real models, to real cases. We don't have a real wind farm that had this issue, but we deal with a specific type of wind turbine in our company here. but we were still able to create some fictive grid conditions for which such conditions, for such adverse interactions appear. And we were able to verify that the DQ scanning was capable of capturing these conditions, yes.
Thank you.
Mm-hmm.
Okay, so I noticed another question from the chat. Okay, so it's very long, so maybe I can read it. So in this approach, you decouple the AC network from the wind farm, then connect the wind farm to a voltage source. So the disadvantage of such approach is that in some cases, wind farm control gain values are modified or adapted online based on weak or strong network. So what would the strategy of this approach to get the frequency response of the wind when it is connected to a weak system?
Mm-hmm. So there is if I understood right, there's more than one question here.
Yeah, maybe.
Yeah, so it's an important point because we have to go back and stress that we are doing small signal stability analysis, and everything that happens here is based on the operating condition that we have for both systems. So if we go back to the simplified system here, we have the grid, which can be very complex, and we have also our wind farm, which can also be very large and have many components. And what we try to do here, and I want to stress this, is that first we try to extract the VD and VQ conditions, or the ID and IQ conditions, from the complete system model. So we do a first, if the model is available, of course, we do a first time domain simulation with the complete grid and with the wind farm, and we wait for the time domain steady state condition to get that VD and VQ0 or ID and IQ0. Then when we separate the system, so that's the interesting part. When I separate the system and I want to investigate, for example, just the grid response at this specific operate condition, I want to remind you that we are still using this extracted ID0 and IQ0 to stress this system before applying the perturbation. So if we're talking, for example, about the grid, that ID0 and IQ0 that we have, they are still being considered here. And that's the closest we can get at the moment from that operating condition that results from the complete system consideration. And for the cases that we investigate, we were able, for example, if we have other controllers here, let's suppose that we have a neighbor wind farm here, as long as you're pushing that power to the system, of course, this ID0 and IQ0, they will result for this first simulation from the controllers being applied in this wind farm. They will tend to bring that grid to that stressed operating condition, which corresponds to the one that we want to analyze. So yes, we separate the systems, but we try to take the operating condition of the system into account by keeping the VD0 and VQ0 or ID0 and IQ0 that we extract from the operating condition. Now to the second question, what is the strategy to get the frequency response of the wind when it's connected to a weak system? So I suppose that at least I try to understand that if we have like a very weak system here and that this first simulation is not possible, right? Then we have already an issue. So if I cannot do this first simulation to obtain the steady state condition correspond to the case in which I want to assess the small signal stability, well, then the system is already unstable and I already have that answer. But if I still want to generate that Nyquist plot for the system, what we did in some specific case was to initialize the system with a load flow. So let's suppose that we have an extreme weak grid here and that this operating condition is not possible for the nominal case. What we did is that we stressed the system with the load flow results, not with the time domain. There may be a difference in there, there may be not, depending on how this is done. But what we do is that we still try to stress the system, especially in the case in which we have multi-converter system. This is extremely important because the stability is done for that specific operating condition. So we still try to stress the system at least as close as we can get to the operation that we have. And it shows up in the Nyquist criterion that the stability is there. So that's the approach that we did. I hope I was able to answer the question.
Yes, I hope to. I'm not a specialist. So now another question. Whether the SSTI, SSCI can be possible to observe due to wind farm if series capacitor is not installed?
Yes. Now that's also an interesting question. We have other cases for which we saw instabilities without the series compensation. Yes, we have also a case for which this happened for a full converter machine without series compensation. But then these were issues related to very weak grid conditions.
Okay.
So we were able to see instabilities also without the series compensation. Yes.
Okay, so it's not okay. So just to come back to the question before, the very long question before, the listener was satisfied.
Okay.
And maybe a last question. Regarding the Nyquist criteria you spoke, what were the critical state variable analyzed?
Okay. There's two parts of the answer for this question. First of all, when we applied the Nyquist, so when we applied the DQ scanning technique for the system here, we tried really to put ourselves in the condition of a planning engineer that is performing the interconnection studies for the system. And in this case, as I mentioned, it's very rare that this person will have the information of what is behind this model of the wind farm. And he usually will not have the time to develop the analytical equations for all the system in order to be able to perform a model analysis and talk about which were the states that were participating at this instability. So basically, when you apply the DQ scanning technique that we outlined here today, you only get the information, there is a potential interaction risk or not. This technique is not capable of telling you which is the critical state. There may be some changes that you can do in your system, or if you have access to your controller, and then you can go in the direction of sensitivity analysis to see, for example, how much a specific parameter will impact the generalized Nyquist criterion. For example, let's suppose that what we were seeing here, this figure, is related to the series compensation. So now what would happen to this figure if I start reducing the series compensation? Well, let's suppose that I go to no series compensation and the system becomes stable. I am supposed not to encircle this critical point anymore. So I can still see it has to do with that series capacitance. Then probably the critical state will be the series capacitance voltage. However, for a smaller system, specific for this system here, we developed the complete analytical equations for the complete system, not only for the grid, for the series capacitance, but also for the wind farm, which was in this case a type 3 wind farm with all the rotor and grid side converter. And for that specific case, and we have to be very careful here not to translate these results to every wind turbine and to every wind farm, but for this specific case that I'm showing here, for the type 3 wind turbines that we investigated, we were able to find that the critical states participating at this critical oscillation, at the instability, were related to the series capacitance voltages and the inductance, in the asynchronous generator used in the type 3 machines. So, the currents flowing through the asynchronous generator of the type 3 wind turbines. So at the end of the day, by looking into the equations, by looking into this complete system of equations, we were able to tell that, again, for this specific case, it was a case of interaction between the inductance of the generator of the type 3 wind turbines and the capacitance of the series compensation.
Okay, thank you, Aris. So we have to close this presentation. So I thank you again for your presentation and for your participation to our conference. So thank you very much, Aramis.
Okay, also from my side, thank you to the EMTP team for the opportunity to share these results with you today. And again, like if there is any further question, feel free to contact me also per email. Okay.
Yes, I will forward you the question.
Okay, thank you
Thank you, Ernest.
for your attention.